Marhaban and welcome to the last presentation on Entity Relationship Modeling for CIS 3107 Database Modeling. We will be discussing database design challenges, which is covered in section 4.3 in our text. In this last presentation, we will learn how ERD components affect database design and implementation, and that real-world database design often requires a reconciliation of conflicting goals. Lastly, we will summarize the design standards used for our course. The process of database design is iterative rather than a linear or sequential process. The verb iterate means, quote, to do again or repeatedly, end quote. Thus, an iterative process is based on repetition of processes and procedures. Building an ERD usually involves the following activities: creating a detailed narrative of the organization's descriptions of operations, identifying the business rules based on the description of operations, identifying the main entities and relationships from the business rules, developing the initial ERD, identifying the attributes and primary keys that adequately describe the entities, and finally, revising and reviewing the ERD. For example, the School of Business and Technology, SB&T, has an accounting department, a management/marketing department, and an economic/finance department, and a computer information systems department. Note again the cardinality rules. The smallest number of departments operated by a school is 1, and the largest number of departments is indeterminate, or n. On the other hand, each department belongs to only a single school. Thus, the cardinality is expressed by 1, 1. That is, the minimum number of schools to which a department belongs is 1, as is the maximum number. Figure 4.26 illustrates these first two business rules. Each department may offer courses. For example, the management/marketing department offers courses such as Introduction to Management, Principles of Marketing, and Production Management. The ERD segment for this condition is shown in Figure 4.27. Note that this relationship is based on the way Tiny College operates. For example, if the Tiny College had some departments that were classified as, quote, research only, end quote, they would not offer courses. Therefore, the course entity would be optional to the department entity. In Figure 4.28, a one-to-many relationship exists between course and class. Additionally, each class is offered during a given semester. Semester defines the year and the term that the class will be offered. Note that this is different from the day when the student actually enrolls in a class. Each department should have one or more professors assigned to it. One and only one of those professor chairs the department, and no professor is required to accept the chair position. Therefore, department is optional to professor in the, quote, chairs, end quote, relationship. Those relationships are summarized in the ER segment shown in Figure 4.29. Each professor may teach up to 4 classes. Each class is a section of a course. A professor may also be on a research contract and teach no classes at all. The ER segment in Figure 4.30 depicts those conditions. Each student may enroll in up to 6 classes, and each class may have up to 35 students, thus creating a many-to-many relationship between student and class. Because a class can initially exist at the start of the enrollment period, even though no students have enrolled in it, student is optional to class in the many-to-many relationship. This many-to-many relationship must be divided into 2 one-to-many relationships through the use of the enroll entity, shown in the ERD segment in Figure 4.31. However, note that the optional symbol is shown next to enroll. If a class exists but has no students enrolled in it, that class does not occur in the enroll table. Note also that the enroll entity is weak. It is existence dependent, and it is composite, or a primary key is composed of primary keys of student and class entities. You can add the cardinalities 0, 6 and 0, 35 next to the enroll entity to reflect the business rule constraints. In Figure 4.32, each department has several or many students whose major is offered by that department. However, each student has only a single major and is therefore associated with a single department. However, in the tiny college environment, it is possible, at least for a while, for a student not to declare a major field of study. Such a student would not be associated with a department. Therefore, department is optional to student. In Figure 4.33, each student has an advisor in his or her department. Each advisor counsels several students. An advisor is also a professor, but not all professors advise students. Therefore, student is optional to professor in the, quote, professor advises student, end quote, relationship. As you can see in Figure 4.34, the class entity contains a room_code attribute. Given the naming conventions, it is clear that room_code is a foreign key to another entity. Clearly, because a class is taught in a room, it is reasonable to assume that the room_code in class is the foreign key to an entity named room. In turn, each room is located in a building, so the last tiny college ERD is created by observing that a building can contain many rooms, but each room is found in a single building. In this ERD segment, it is clear that some buildings do not contain classrooms. Once you have discovered the relevant entities, you can define the initial set of relationships among them. Next, you describe the entity attributes. Identifying the attributes of the entity helps you to better understand the relationships among entities. Table 4.4 here summarizes the ERM's components and names the entities and their relationships. Database designers must often make design compromises that are triggered by conflicting goals. The database design must conform to design standards, which develop logical structures and minimize data redundancies, thereby minimizing the likelihood that destructive data anomalies. In many organizations, particularly those that generate large numbers of transactions, high processing speeds are often a top priority in a database design, which can limit the number and complexity of logical desirable relationships. The quest for timely information might be the focus of a database design, and the need for maximum information generation may lead to a loss of clean design structures and high transaction speed. Note that the employee_V1 table in Figure 4.38 is likely to yield data anomalies. For example, if Ann Jones divorces Anton Shapiro, two records must be updated by setting the respective emp_spouse values to null to properly reflect that change. The second implementation would be to create a new entity shown as married_V1 in a one-to-many relationship with employee, but does not eliminate the nulls for employees who are not married to other employees in the same company. A third approach would be to have two entities, marriage and mar_part, in a one-to-many relationship. Mar_part contains the _num foreign key to employee. However, even this approach has issues. It requires the collection of additional data regarding the employee's marriage, the marriage date. As you can see, a recursive one-to-one relationship yields many different solutions with varying degrees of effectiveness and adherence to basic design principles. Our CIS 3107 data modeling standards are now updated to include standards from Unit 4. Conservative use of required fields with required fields bolded. Conservative use of mandatory relationships with indication as part of the crow's foot notation. Identifiers are underlined in the ERD. Weak relationships use a dashed line between entities, while strong relationships use a solid line between the entities. In this third presentation, we have discussed ERDs may be based on many different ERMs. However, regardless of which model is selected, the modeling logic remains the same. Because no ERM can accurately portray all real-world data and action constraints, application software must be used to augment the implementation of at least some of the business rules. Unified Modeling Language, UML, class diagrams are used to represent the static data structures in a data model. The symbols used in the UML class and ER diagrams are very similar. The UML class diagrams can be used to depict data models at the conceptual or implementation abstract levels. Database designers, no matter how well they can produce designs that conform to all applicable modeling conventions, are often forced to make design compromises. Those compromises are required when end users have vital transaction speed and information requirements that prevent the use of, quote, perfect, unquote, modeling logic and adherence to all modeling conventions. Therefore, database designers must use their professional judgment to determine how and to what extent the modeling conventions are subject to modification. To ensure that their professional judgments are sound, database designers must have detailed and in-depth knowledge of data modeling conventions. It is also important to document the design process from beginning to end, which helps keep the design process on track and allows for easy modification in the future. Thank you for watching our Unit 4 Part 3 presentation. The diagrams and content of this lecture were derived from our textbook. For more detailed treatment of these concepts, please review pages 140 to 152 in our textbook.